today's session, and the first speaker is Vincenzo Vitelli.
Thank you. Well, I wish to thank the organizer for the opportunity to attend this workshop, actually these twin workshops, and speak here. And indeed, I'm hoping to give in this talks two talks effectively, one on chiral symmetry breaking in confined nematics, and one on nonlinear acoustics in ultra-soft materials, which I believe gels, which are of interest to our twin workshop, elastomers, and perhaps there's also some intriguing analogy with smectic liquid crystal following yesterday's talk by John Toner. But let me first start with this topic, the chiral symmetry breaking in confined nematics. And I'd like to tell you that any experimental image that you'll see in this talk is the result of the work done in the lab of Alberto Fernandez Nieves. You can see some of his student and postdocs listed here. And we are trying to do some modeling to explain what Alberto was seeing. I'll tell you in more detail momentarily. And the main driving force behind it is Vincent Koning is also in the audience and is a final year PhD student. And we have restarted our collaboration also with Randy Kamian, whom you know and is in the audience too. So I would like to start this talk by asking, what is Alberto Fernandez Nieves attentively staring at? So what is, I don't really know because I didn't take the picture, but I like to think that what he's looking at is his new creation. Alberto has managed to construct droplets, which he's been doing for a while, for a few years, stuffed with liquid crystals. But the peculiarity of these droplets is that their shape is either toroidal or shapes with multiple handles, like this pretzel shape or this multiple hole shapes that you see in there. And as soon as he realized that, he started seeing a wealth of interesting defect structures and director structures that he wanted to explain and understand. And there's some interesting parallel with the elegant presentation of Smaliak yesterday. What Ivan does is he constructs colloids, which are much smaller than this nearly millimeter-sized objects, but Ivan essentially puts the nematic outside. So it's still anchored to the surface, but it's like the out of the surface problem. And the first thing I would like to tell you, even if Alberto would have done a much better job than me in doing this, is to tell you a little bit how he managed to do this thing, starting from the single torus. And I think to some extent, this is one of the neatest aspects of his work. So this will be a bit of a superficial explanation of all the tricks that he had to devise. But the problem that Alberto was facing in trying to make this toroidal droplets, which he did not face when he was studying spherical droplets, is that a torus is not favored by surface tension. And so somehow Alberto had to convince liquids to behave like solid, like a mold. And so strictly speaking, what he did is precisely that. He said, well, I'm going to stick a needle. And so far, it's the same technique that he was using in his previous microfluidic studies of double emulsion with spherical surface. Inside, and this is a crucial part, a yield stress material. And then he rotates, if you like, either the needle or the base on which this is put on. And as he rotates it, of course, he presses it on the needle, injects the liquid crystal. This makes a toroidal droplet. And at this point, the thing would break if the material in which, this very special fluid in which he puts this stuff was not strain stiffening, meaning that the moment in which it stops rotating and takes the needle out, the material starts becoming immediately like a solid because it's no longer stirred. And so it becomes a mold, a solid mold on the time scales of his experiment, inside which the nematics can be trapped. And he did a lot of interesting work to figure out the chemistry to make sure that the anchoring of the nematic at the surface was tangential. Okay? And once he achieved all of this, he came to us unhappy. And why is that? So, well, not unhappy, but a bit surprised by what he had found. So just think a bit, aside from the experiment of Alberto, what you would imagine a nematic does in a torus. Okay? First of all, the torus, the one-hole torus, single-handle torus, is a surface that with tangential boundary condition does not require defect in it. We'll get to the topological constraints later. So probably the simplest guess that you would imagine is that if the director depicted in black here wants to be tangential on the outer surface, what the director will do is to just take this untwisted configuration, which will cost some band energy, and that would be probably the easiest guess. Now, Alberto knew better. He knew that, for example, when you study DNA tori or also the torons of Ivan, you can indeed see a twisted configuration. And I'm going to explain for the people who are not into the physics of this structures exactly how that comes about momentarily. But what surprised Alberto a lot is that he was expecting that he would have been able to get from this structure to this structure by changing the aspect ratio, the geometry of this tori. In particular, the ratio between the outer radii and the inner radii of this torus. In other words, by making the torus slender or fatter. And he kept changing all these parameters experimentally, and he could only find the twisted one. So there's something in his experiment, this is his puzzle, that seems to stabilize the twisted face such that we effectively never seen the untwisted one. And so the question that he had for us was, guys, can you please come up with some plausible mechanism to achieve that? Okay? And here is where Vincent Koning stepped in this picture, and he started constructing what is perhaps the minimal model to understand liquid crystal elasticity in confined spaces, which is he set up a Frank free energy. We all know what the Frank free energy is. But what Vincent insight was is that he wanted to include, because he understood the crucial role of boundary, the so-called saddle splay elastic term. Now, this saddle splay elastic term is deeply steeped, I forgot what the word is, but it's been very important in the physics of liquid crystal. The existence of the blue phase, as reviewed by Kates yesterday, depends pretty much on the existence of this boundary term that gets evaluated at the boundary between the three tubes that he was showing. This is a classic calculation of set. And so we know that the saddle splay term is important. What I want to show you here is how it's also responsible for stabilizing this configuration, we believe. And of course, for the splay, twist, and bend, you have a simple pictorial representation of what they are, so you can associate some intuition to it. And in order to move on in this talk, it seems to me that it's useful to understand how can we think about the saddle splay in equally pictorial terms. And of course, you can do it in a couple of special cases. Perhaps the easiest would be a cylinder or the torus, which is what we did. Or you can do it in more general terms. And this is one of the things that we will write up in more detail in that paper with Randy that is still not come to fruition. So what I would like to tell you is this. So as you noticed, it's convenient to write down the saddle splay elastic term as a surface term. Okay? Now, we know that by chemistry, the boundary conditions are planar, and there is an easy axis in the plane in which the nematic director can rotate. Okay? The question that we asked is, can we think of the saddle splay as an effective anchoring term at the surface, such that from the competition of this anchoring term and the bulk terms, we can understand the source of these twisted structures. And so the general recipe, sparing you some of the details, is that if you have a general surface, here is this saddle-like structure that resembles the inner part of one of the tori, the prescription is the following. You identify the principal direction of curvature on the surface. Let's say it's K1 in this case, which is in which the radius of curvature is the smallest, so the surface is the most curved. On the cylinder, it would be this direction, of course, because the other one has no curvature. On the tori, it will still be the small radius. And then you want to align your director precisely in that direction. Okay? And any cost of going away from that direction will cost quadratically in the angle that you form. In general, and this is actually where this equation resembles a lot something that Randy and I were doing when we were studying symmetrics on curved crystals. We understood the coupling of the nematic director, or the perpendicular to the symmetric layer, to the extrinsic curvature of the surface, which takes exactly the same shape. And here probably a reference to a paper that we wrote with Chris Santangelo and David Nelson could have been appropriate. Okay? So just to simplify, if you had the torus, there is a bulk energy that want to align along the axis of the torus, and this saddle plate that want to make it aligned along this radial direction, and the competition between the two will cause something fun in the system.
It depends on the sign of K24, doesn't it?
It depends, absolutely. It depends. So the sign that I'm talking about is the sign that happens in reality. Huh? Well, one way to be sure is to look at the outcome of this experiment. In fact, the outcome of this experiment towards the end will give you some hints, also the magnitude of K24 that you can compare with, if this explanation is somewhat correct, that you can compare with other experiments that some people have done, including here in the audience. Now, so how do we proceed here? So the way we will proceed, this is a manifesto slide, and I'll show you the details momentarily, is that we would like to write down an ansatz parametrized by the angle labeled as omega, more or less, that the director will make at the outer edge of this torus. So if omega is equal to 0, you have a structure which has absolutely no twist, but depending on the sign of this quantity, you can have either a twist in one direction or a twist in the opposite direction. And one of the things that Vincent was able to do is to essentially map this problem on the problem of an Ising model near phase transition, in which the role of the twist is, the role of the magnetization is played by twist. In other words, a spontaneous symmetry breaking setup. So how do we do that? Is to say, okay, we write down an ansatz in terms of this parameter. You'll see the ansatz in the next slide. We plug it back in the nematic free energy with all those 4 terms that you saw in the previous slides. And then we're going to get an expression for that energy, which has a term that depends on the elastic constant and the aspect ratio of the torus. That is to say, the ratio between the outer and inner radii. This is geometric control parameter for that transition. A quadratic term in omega squared, and a quartic term. And then, depending on the sign of this term and that term, you can have either an omega equals 0 or an omega different from 0 phase configuration to be favored. So this.
Perhaps you said that already. Is there like local, like an angle or something with global measure of
So it's if you like, it's a parameter. So this is a double twist configuration. So this parameter essentially labels the texture, but it doesn't mean that the texture is twisted by that amount everywhere in the same. In fact, as you saw in the previous one, as you move inside the torus, eventually the nematic director becomes axial. Okay? But as you move out, there's this interesting dependence. And of course, perhaps without getting too much in details, again, this is the ratio, the geometric control parameter. Here is our ansatz, which has a variation of parameters. And the only thing to remember from the slides is omega determines the degree of twist. Omega equals 0 is this, and omega different from 0 is this other configuration. Okay? And now what I want to show you, okay, there's the ansatz, which is some interesting property, but let me not get too much into that. What I would like to tell you is that once you plug this back in, there is an energy that you derive. And I would like to explain what that energy tells you and how do you map it to this standard setup from the theory of phase transitions. So let me first tell you what the symbols are. So again, some of them I mentioned already, but we also defined a dimensionless coupling constant, nematic constant that is K2 minus K24 divided by K3. Just to remind you, this is what we mean. K2 is the twist, and K3 is the bend, and K24 is the other one. So let's see. The game here is this. Clearly, I'm just going to say it in words and then show you the equation. Clearly, if you have a twist configuration, you have to pay a cost in twist energy. Okay? But also, if you have a bend configuration, you have to pay a cost in bend energy. Now, the trick here that you'll see is that when you start twisting, of course, you start paying more in twist energy, but you lower a little bit the cost in bending energy. Okay? K24 gets in the way because it screens the elastic cost of twisting, making twisting extremely cheap. So it's always favorable, or becomes favorable over a vast range, to introduce twist at the expense of bend. Now let me show you how the equations tell you that story. Let me go back. So this first term is independent of omega, so we don't really care. Let's look at the quadratic term. And what we want to know is under what condition the quadratic term switches sign. Because when that happens, you go from wanting an omega equals 0 structure, which is like arrow, to an omega different from 0 structure, which can have these two minima, which Alberto keeps seeing all the time. Now, this term here, especially when you multiply it by K3, reduces, if you ignore K24, purely to a cost of twist. And it's telling you that the cost you're paying for twist is quadratic in omega squared. But as soon as you start paying that cost, you also reduce the bending cost. And exactly when the two balance, you have this point here. Now, this is the same reason why this happens also in toroidal DNA, for example. The role that we need to incorporate here for subtle splay is that, as you can see, the subtle splay constant renormalizes, if you like, or reduces the cost of twist. So whenever K24 is comparable to K2, which experimentally is precisely the range that you have, then this twist can cost effectively no energy, or very little energy. Okay, so this is the idea. And of course, there is a spontaneous symmetry breaking highlighted by this picture. Notice that the other term is always positive definite. Now, I should say that these conclusions are based on an ansatz. So we did some numerics to make sure that we got it at least qualitatively right. What you can also do is you can construct a phase diagram. A phase diagram will tell you whether you have this configuration or that configuration, depending on the slenderness, which is how fat your tori is. This is the parameter that Alberto kept changing in his experiment without seeing any effect. And the ratio between K24, which we consider the culprit for what's happening here, for the stabilization of the twisted phase, and K2, which is the cost of twist. And in particular, notice that whenever K24 becomes very comparable to K2, no matter what aspect ratio you pick up, you always see this twisted configuration. Indeed, if you trust your ansatz, perhaps a little bit more than it would be legitimate to do, you can calculate the twist angle from the ansatz as a function of aspect ratio and compare it with the experimental points that Alberto measured, and fit, essentially, the value for K24 that you would obtain. Of course, the fit doesn't work particularly well for fat tori, but it tells us a story which is consistent in terms of the value that we observe for K24, with the notion that K24 and K2 are very close in magnitude in this liquid crystal, which is 5Cb.
You simulated in very large aspect ratio domains, starting from the critical point?
Yes, so you saw in that so for the simulations at the moment, so simulation are two things. There's a starting from the ansatz and do an energy minimization and then Monte Carlo. So the energy minimization is a bit easier, we've done more. There we have spanned, as you can see, a very vast range of degree of fatness. And we find
I was trying to understand whether you've seen any chiral phase ordering.
chiral phase ordering?
You start with the isotropic state, it's going to symmetry break into left and right-handed versions.
Yeah.
And potentially order
Right, so but what you're really describing is a situation in which you start like a coarsening process. So this, we could possibly see it in the Monte Carlo, but not in the energy minimization yet. So we're in the process of doing it. This is interesting because there could be also domains, which look like static solitons in these things. So yeah, we are working on that, but we haven't. Martin Bates, who's also a co-author of this work, is helping out with those type of simulations. I would like to say a word, especially in this context, where this topic has been covered a lot, especially by Ivan, but also many theory talks before, that clearly the moment in which Alberto goes from the single toroidal droplet to a double toroidal droplet, triple toroidal droplets, he cannot get away without nucleating some defects. This defect, as explained by several people, must satisfy essentially some global constraints that derive from the curvature of the bounding surface. I believe that this experiment per se doesn't have all the accuracy to detect all the possibility and to really image it very, very well. But one of the things that Alberto has already been able to see is that in this double tori, that in the language of Smaliuk has negative curvature and a topological index equal to -2, which means that you want to put in, say, 2 -1 hyperbolic hedgehog or 4 -1/2, you can already see that the negative defect, and here you really have to look at only the projection to the surface because there's limited access that Alberto has to look at the details in the bulk. You can already see under cross-polarized that there are 2 -1 defects located precisely in this ring where the curvature is the most negative. They don't sit here because here the curvature is less negative. But of course, when you start playing games with something like this, now you have 3 handles. So by the Poincaré-Hopf theorem, this index is really -4. And so you have 3 places to put your defect, but you have 4 units of topological charge to put in. And so the system chooses to put them in one of these necks, and 2 of them are closely trapped. I should say that the energetics of this structure, in my opinion, both in this problem and perhaps to some extent also in the studies in the outer problem, need to be studied in more detail. Meaning it's clear that many of these energy configurations have more or less the same energy, but there could be some interesting property of how the energy changes when you change the size of your bounding surfaces. Here we go, and this is actually the thing that makes Alberto excited. You go to the size of millimeters when you make this toroidal droplet. In the case of Ivan, I think the colloids I would imagine are, please help me, a couple of microns, which of course these scales are gigantic on the scale of the liquid crystals, but there could be interesting property of how some configurations are favored over others. So there's quite a lot of computational work, in my opinion, that needs to be done here.
So the liquid crystal here is 3-dimensional, right? And it's feeling like...
Yes, absolutely. So it's not just on the surface. That's why these theorems are not the whole story, because they only tell you the projected part of the nematic director on the bounding surface. You can also...
I was wondering whether I did one.
Being 3-dimensional, is there should I think about like a line going from, like, say, the -1 to the -1?
Right.
So is there some...
Well, that's the point I was alluding to. So it can be either 2 Bojums, or if you like, half hyperbolic hedgehogs, or there could be lines going inside. But it's difficult in this experiment to detect that if you're looking mostly under cross-polarizers at what happens at the surface.
But then in the case of the 3
For example, he
torus-
showed the cases in which you have the line going in the 3rd dimension, in the bulk, and the splitting possibly also.
in the case of the 3 torus, that will give you something interesting in the inside
Absolutely,
of the...
absolutely. There will also be an interesting effect coming from the fact that if this structure is a chirality, in the middle you don't know what happens. It's sort of like a domain wall of chirality, even in the double torus. And this is one of the things that we're studying that is interesting. So I would like to stop here this discussion and literally switch gears and tell you about something that it's completely different in spirit in 2 ways. The first one is, if I can get it started, the first one is that most of what you've heard started really with an experiment, and we tried to explain it. In the second part of this talk, I would like to throw some ideas at you that I believe are they've not been tested experimentally yet, but I believe that could be interesting in the study of well, gels for our friends that come from the other seminar, but also elastomers. And there will be a talk by De Simone following mine soon that I think will complement very, very well these things. So what do I want to tell you? I want to tell you about, well, I want to go from topological matter that we discussed up to now to something that I like to call fragile matter. And in fact, I would like to tell you about problems of nonlinear acoustics in this media that I call fragile. But I would like to start from something that is disarmingly simple, even a bit banal. If you take a spring and you touch one end of this, what you're seeing here, it's a pulse of energy. Not particles moving, but energy moving across the spring. If you gently touch, the speed at which that pulse moves is just the speed of sound in the spring. It's given by the square root of the spring constant, the square root of the elastic moduli of that material. By contrast, it's only when you really whack things hard that you can generate a shock in a material or a solid. In solids, it's very hard to do that. In fact, when I type in Google shocks, the first thing that comes in Google is a jet like this one. And even a jet has a hard time, because the jet still has to move faster than 330 meters per second, which is pretty fast. If that jet was moving in steel, it would have to move faster than 6,000 meters per second. That's why the study of shocks in solids is really reserved to a couple of applications that usually you don't want to know about, for example, explosions. So what I'd like to tell you today, and this is the subject that I like to refer to as fragile matter, which is the extreme on the softness domain. It's solids that at some level, because of some interesting aspect of their architecture, can behave in a way which is softer than air. Okay? And so you could ask, well, what are these exquisitely exotic systems? Well, it turns out that pretty much anything you can think about can be brought in that state. And Tom Lubensky in his lecture gave us some models that have those features. But let me tell you that if you have a glass, a covalent network glass, or a network glass emerging from liquid crystal structures like the one that Kate was discussing yesterday, possibly, or if you have gels and elastomers in which you can change the amount of cross-linking. In the glass, you just change the coordination number of this network, or granular media under decreasing pressures. All this medium have a knob inside that allows you to do the following: to send the elastic moduli and the relative speed of sound essentially to zero, or to make them very, very low. For example, you know in elastomers, they're notorious for having a super soft elasticity. Okay? Now, think about it. If the speed of sound gets close to zero, and to give you an example, in the tissues of your body, the sheer speed of sound can go down to meters per second. It becomes extremely easy to break the sound barrier. And if you're really at the critical, at the point in the structure of this material when the speed of sound goes to zero, everything must propagate supersonically. The excitations of this material are no longer phonons, but something completely different. And I would like to start telling you this story and draw some parallel also with the absorption of ultrasound that John Toner was talking yesterday in the case of nematics. So it's useful to start with something concrete. Tom Lubensky gave an example, or detailed discussion actually, of the notion of isostaticity. So I think it may be good to just recap it very quickly, because I don't know how many people were there. So what Tom was saying, really building on the shoulders of Maxwell, is that if you have a system, let's say just with central forces, but you can generalize to bond bending, if you want to know whether a structure is rigid or not, what you're doing is you're matching the number of degrees of freedom, which per particle will be just the dimensionality of your sample, with the number of forces between particles, say on average. So the springs on average that emanate from each node. That is the average coordination number of the network divided by 2, because each spring is divided by 2 of them. Whenever you saturate this constraint, you reach a critical number called isostatic one, such that if Z, the mean coordination number of your sample, is greater than ZC, you have something that is rigid. If you are below ZC, you become floppy. Okay? Now, an example of a fragile system is a system in which you are right at ZC, right at threshold. So in this talk, I would like to understand what happens close to the threshold and how you can explain the behavior of some real materials in that way. So in a gel, for example, you can tune the degree of connectivity by changing the amount of cross-linkers. Okay? Elastomers have this property too. Now, the thing that we all learned in solid-state physics, which is a bit the other way around compared to what I'm going to be doing in this talk, is the following, is that whenever you study the solid state, you say there is an Hamiltonian, which is an harmonic part cast in terms of the strain energy, the strain field. And if you have a lot of stamina, you consider anharmonic contributions, usually assumed to be small. Underlying this paradigm is the fact that if you forget entirely the anharmonic part and you diagonalize the harmonic part, you get some basic excitations, which we like to refer as phonons or vibrational modes. Tom showed examples in the structures. This is certainly an approach that works like that when Z is much greater than ZC. But if you take this same network here, and the only thing that you do is to dilute the connectivity by cutting some of those springs. Just look the tiny change. Okay? So it's more diluted. And you go right at threshold. So right at ZC, when the solid has just enough constraint to be rigid, but no more than necessary, then the elastic moduli can go to 0, which means the prefactor of the harmonic part of your Hamiltonian goes to 0. Simple example, in a square lattice. In a square lattice, if you try to shear, the cost of shearing is 0 if you concentrate only on deformations, which are small. So the shear modulus of a square lattice is 0. Once you start adding crosses, as Tom was doing, of course, you pick up an extra cost that depends on the amount of crosses that you're putting in. But in that situation, the problem has changed the structure. You have an anharmonic part of your energy and an harmonic part, which is vanishing. So if you want to understand this physics, the physics of ultra-soft solid, you have to, if you like, find the excitation corresponding to the anharmonic part, which are going to be shocks or solitons, which replace the phonons. And then, if you want to go a little bit above the critical point, where the majority of the experiments are performed, you have to reinstall perturbatively the harmonic part. So it's the other way around from how normally people proceed. And it's a little bit harder, as some of you can guess. But this is precisely what we will do. And so we will first figure out the shock and soliton at the critical point, perturb away from it, and understand situations in which you have both the linear and the nonlinear physics, and we will parameterize the distance from the critical point as the difference between the coordination number of your network minus the critical coordination given by the isostatic criteria in dimension d equal 2. That is the plan. Is the logic clear? And so now I want to show you how you do it concretely in an example. And in my opinion, the question, for example, how this would work in liquid crystal elastomer is open. And I want to provoke the expert in the audience to think about it. I'm going to talk about isotropic systems only here. OK, so let's start with a movie, which is a bit more fun. This movie is exactly an isostatic network as close to the critical, a nearly isostatic network, as close to the critical point as we can create it. And essentially has a vanishingly small shear modulus when the distance from the critical point, delta z, goes to 0. The prefactor in front here is k, which is the spring contrast of your material. And you also have some viscosity given by the relative velocity between two particles times a coefficient, a microscopic coefficient of dissipation. And now what I want to show you is what happens when I shear one end. Now, in a normal solid, first of all, you would know what happens, because in a normal solid, there would be a front moving at the transverse speed of sound. But the transverse speed of sound is 0 here. So what happens? So we did a simulation, molecular dynamics. So what you see, and Stefan Ulrich, who's the hero here of the story, a postdoc in my group, is color-coded this particle. In yellow, the ones that are moving at a finite speed in the y direction, while the boundary is moved at a constant speed v0. And here we colored in blue the ones which are static.
Do you have free boundaries or periodic boundaries?
So in this direction, there is this Lees-Edwards boundary condition, which is essentially we're doing periodic boundary in shear. And so here is pinned because all the particles move coordinately at velocity v0. And this edge is less important because we never look until you reach there, the strain reach there. And I don't know if this movie is clear to everybody, but there's a part which is sheared, a part which is not sheared. This is normally most system is a transient. You only care about the end when the shear is established. But in a system in which the speeds of sound are ultra slow, the transient may be the best thing to look at if you want to understand the viscoelastic behavior of these materials. So what we're proposing this, especially when we talk with our experimental friend, is an idea that I like to refer to as shear front rheology. You watch the velocity, the velocity at which that front moves. You watch the width of that front that separates the sheared and unsheared part, and from that, you extract the viscoelastic behavior, linear and non-linear, also oscillatory rheology from this experiment. Okay? But also at a practical point, from a practical point of view, a simple question that arises before going into showing the equivalence of shear front rheology and oscillatory rheology is, what sets this damn speed? It cannot be square root of g. Okay? So there's only one thing left, which is the reason why I refer to this thing as strongly nonlinear waves, which is the amount you're straining your boundary. You see, the difference between linear and nonlinear is that a linear wave has a speed given by intrinsic property of the medium. A strongly nonlinear one has a speed which is set by how hard you're driving your system. So how hard you drive your system is determined by this parameter, which is actually a field called gamma, which is dy dx. So it's the slope of this line. Which,
not a speed, though,
huh?
it's not a speed.
No, in fact, there's two separate discussions that you have to do here. There's the velocity at which you drive this boundary, and there is the strain. One tells you whether you're linear or nonlinear. The other one tells you whether you can use the quasi-static approximation or not. And one pertains to elasticity in the DC limit. The other one pertains to the frequency depending on the elastic moduli. I'm first going to do the regime in which you're driving sufficiently slow that you forget the time dependence. What I want to show you in this medium, and I'll see how far I can go, so let me advertise the answer. 3 key assumptions used in elasticity breakdown. The linear response assumption, this I've already seen, the affine response assumption, and the quasi-static assumption. All of them break down simultaneously as you go to the critical point. So you have to be careful how you deal with that. First thing that we did is we say, look, plot the velocity of the front versus the velocity of the front versus the strain, and tell me what the answer is for an arbitrary system, for a system at an arbitrary distance from the critical point.
You don't need able to make that observation in your computation at a single instant. You're only able to make that observation at a single instant.
Which observation?
The observation of the velocity as a function of gamma,
Well, no, so what we do is that we track the displacement of this front in the x direction as a function of time until you achieve a constant speed. You're driving at a constant, remember, speed also the boundary. You track that velocity as a function of gamma and as a function of delta z. Okay? So there would be a plot with 3 axes. Instead of doing a plot with 3 axes, I don't know if this is more confusing or this is less confusing. If I can only get my computer to move, it would be, yeah. What we did is we plotted the velocity of the front as a function of gamma, and these dots are numerical simulation referring to samples at different distances from the critical point. This sample is the softest of all, okay? And there's notice that all of them collapse on these theory curves that we derived in a way that I want to tell you momentarily. There's one first feature that arises from looking at this curve. There are 2 regimes. One in which the velocity of the front is nearly independent of gamma. This is the linear regime. Okay? And then there is the nonlinear regime where the velocity of the front depends on gamma as a power law. Okay? Notice that a slightly unpleasant consequences of wanting to collapse everything on a single curve is that you're measuring velocity in units of topology, which is pretty weird. No, we are rescaling everything by delta z to the 1/2. In reality, the story is that we are rescaling everything here by the linear speed of sound in that medium. Since we know that the shear modulus goes like delta z, the square root of the shear modulus, which is the transverse linear speed of sound, is delta z to the 1/2. So when we divide it by this axis, all of them collapse in the single line. But notice, in order to get full collapse, you also have to rescale gamma by something. And you want to know what is this something? Because that tells you where the crossover between linear and nonlinear takes place. And also you would like to understand this exponent. Or if you're an experimentalist, you would like to know, if I can make a plot like this experimentally, how do I back up the nonlinear rheology from that plot? So the other way around. And what I want to show you is that in this system, that plot is equivalent to the stress-strain relationship. So stress in this system is given by the strain times the shear modulus plus a nonlinear term. This 1/2 here implies that the nonlinear term will be of this form, which is a rather unusual form, only allowed by the fact that you're close to a phase transition because it's non-analytic. How do you see that? Well, if you take the stress and you divide by gamma, you can define an effective shear modulus, which is the normal shear modulus plus, if you like, a nonlinear correction. In the strongly nonlinear regime, or if you prefer, whenever this term is stronger than that, which is certainly true when delta z gets very small. In fact, whenever gamma is greater than delta c, gamma greater than delta c, which is in this regime, this can be ignored, and the square root of the effective shear modulus, we tell you the transverse speed of sound, is just gamma to the power of 1/2, which is precisely what you see here. Most materials have gamma to the power of 3, because it's more it's analytic and compatible with the requirement that sigma should go into minus sigma when gamma goes into minus gamma. But this is an example of how you see the nonlinear rheology. Now, in the final minute or so, I want to tell you that there is another thing, and let me tell you that these things are observed in real material, in particular in biological tissues, for the reason I told you before, because they're so soft in shear. And they will be seen also in other materials that have that feature. Now, one thing that I want to conclude is to say that you can also learn about the viscoelasticity, or the viscosity, which is the most important part. In particular, you look at the width of this front, and I cannot really tell you all the details because I'm already ahead of time, but the width of this front is proportional to this viscous coefficient. So as a function of time, this width increases as depicted on the next slides. But a long time, it starts broadening diffusively, as you can show from writing down the equation of motion for this. So if you plot the width squared divided by time, it will give you an effective viscosity for your medium that you can plot as a function of delta z, which is the distance from the critical point. And what you find is that that viscosity diverges at the critical point. So the system, and here is the, really the most cool thing, in my opinion, the coolest thing, in my opinion, about the system. You remove constraints, and your system becomes more and more viscous. You may ask, why is that? This is the opposite of glasses. Okay? And so we did something funny. We said, well, set the microscopic damping coefficient to 0, so kill damping altogether. This should give you super flat front. And what we find is we find the same thing again and again. Okay? And so we asked ourselves, what is the origin of this effective viscosity that is going to infinity? And here is the analogy with the Tolko toner. In this system, there are soft fluctuations which are due to the non-affine nature of the response of the medium. Let me show you what non-affine means. It means that if you take, well, first let me tell you what affine means. If you work very far from the critical point and you shear the edges of the sample, notice that the deformation that you apply at the boundary gets projected inside purely by geometry. There's no, look at that movie if you can. Notice that what is inside moves exactly like the boundary. But now contrast what happens if you go close to the critical point, which is in a diluted system. You see that inside that there's a lot of motion in the y direction, even if the boundary is sheared only in the x. Yes. Okay? Do you see those fluctuations? So what you're doing, there's a strong absorption here because as you shear your medium, the response inside, or the energy that you put on the shear coherently, gets sucked up or leaks into these fluctuations. The amount of this fluctuation diverges at the critical point, hence giving you an effective divergent viscosity that is attenuating your pulse. This is the same mechanism as in the problem of symmetrical toner, but in this case, it's of course an ordered system, and in particular, in this case, is the soft ondulation of the layer, which are the soft direction compared to the compressive one. Well, I think I'm already over time, so let me not be overly optimistic as to what I can cover. I didn't tell you what happens at early time, super diffusion versus diffusion in the system, but here are some conclusions. And thank you very much for your attention. Thank you. Thanks.